Hello students, your physics teacher Hassan Darwish with you. In this video, and this could be the last video about chapter 8, I'm going to explain the power distribution in a coil magnet system. Let's start. So this is the coil represented in the form of equivalent generator. Here it is, and this is the external circuit. Okay, remember? Here is the coil, and this is the external circuit. And there is a relative motion between the coil and the bar magnet. And as I said, the coil acts as generator. Why? Because it simply sends electricity, maintain voltage. Okay? Now this generator has an EMF E and internal resistance R. But this generator, converts the mechanical energy of the relative motion between the magnet and the coil into electric energy. Unlike the battery, as you studied in first secondary, which changes the chemical energy of the chemical reaction into electric energy. We want to see in this video how the electric power is distributed within this electric circuit. First of all, we know that the electric power input to the external circuit between P and N is by definition P equal UPN times I. And let me emphasize here on the word circuit. This is the power available to the external circuit, okay? But you know that UPN is minus RI plus E. Let's replace here. What do we get? P equal, this is power of the circuit, minus Ri plus Ei, EMF times the electric current, okay? The current in the circuit. Suppose it's like this at some interval of time. So P equal II, this is the first rule, is the rate of conversion of non-electric energy, here mechanical energy, into electric energy within the source. Why? So P total, let me call it total, equal E times I, all this is E times I, is the total electric power created or produced in the coil due to the relative motion between the coil and the magnet. So the conversion of mechanical energy into electric energy. You know this rule, P equal Ri squared. This is the heat power dissipated in the source, I mean in the coil, by Joule's effect. You know this. Okay? So the remaining power or remaining energy available to the external circuit here is UPN times I. Clear? So you can say P total is equal to P available to the circuit, which is U times I, plus P heat, which is the heat power dissipated in the wire of the coil. Okay, any problem? Let's make some application. Application, alternator. What is an alternator? You know alternator. You've learned many times, or you've heard many times about alternator. You see here, alternator is an AC generator. This is the coil, and this is a flat rectangular coil, and this is a U-shaped magnet, which maintains uniform magnetic field from N to S. Now you rotate the coil. That's what happened in the first experiment here. Let me go back here to the beginning of the lesson. You see here it is. This example, we solved an example on it. here in this experiment, remember, when we rotated the coil inside the magnet, okay? Just remember, here is the coil, the magnet, and this is the coil inside the magnet. Now what we are going to do is rotate the coil inside the magnet. We have in this case variation of magnetic. You see the rotation of the coil inside the magnet. We have variation in the magnetic flux, so we have an induced current. This induced current passes in the lamp, and so the lamp glows. Okay? So this is called alternator. Here it is. Now, this is the coil. Here we have slip rings, and these are called carbon brush to transfer the electricity from the coil through the slip rings into the lamp here. Here is the lamp. And in our experiment, we've connected here between the terminals A and B. The external circuit is what? Is a lamp. Of course, it could be a refrigerator, washing machine, fan, anything, resistor, okay? This is a principle of generator, AC generator. Now, the motor functions in the same way, but opposite to the AC generator. In this motor, AC motor, we have the same here, magnet, NS. We call it stator, and because this is static. And the coil turns, we call it rotor. But here, we don't want the coil to give the electricity and acting as generator. The coil is connected to the external generator, okay, DC generator, which gives electricity. Now, when this generator gives, say, for example, electricity, suppose the current is in this form, then remember the electromagnetic force. If a current carrying conductor is placed, like this wire, is placed in a magnetic field, then the wire is subjected to an electromagnetic force. Remember, F equal ILB sine theta. Remember, F equal ILB sine theta. This is the electromagnetic force which acts on this conductor due to the passage of the electric current I, not induced current I, coming from the generator and lying in the magnetic field of the magnet. So let's see through this video made by someone, okay, how the motor acts, okay. Let me okay, sorry. That's the principle here. We have here the flat coil. Clear? This is the flat coil which lies in the magnetic field between the poles N and S. Now look at the brushes which allows the electricity to transfer from the battery to the coil, or in the case of an AC generator, from the coil to the external circuit. You see, this is uniform magnetic field, B. Here is the external DC battery, DC generator. Now, the battery will send a direct current. Now, because the current passes in the wire, and the wire lies in the magnetic field, it is subjected to an electromagnetic force. Here is the force on this part and the force on the other part. Okay? To know the sense of this force, you have to apply what we call right hand rule. F-I-B or FBI, some people call it. You see? And the motor function in this way. That's enough. Now you know the principle. Let's solve some direct application about the motor. So here we have a motor with a rectangular coil of area, that's the area, as equal 0.06 meter times 0.04 meter, and number of loops equal 100. The magnitude of the magnetic field is B equal 0.2 Tesla. Determine the average induced EMF. Here in the motor we call it back EMF because it acts against the EMF of the external generator. Okay? When the rotational speed, this is theta prime, is 1200 revolution per minute, we are given the average value of sine angle 2/pi. Okay, let's start. So we want to find the EMF. Is there a rule for the EMF? Yes, by applying what? Faraday's law. So Faraday's law, E equal minus derivative of flux crossing the loop or linking the coil. So minus phi prime. But we know that phi is equal to NBS cosine theta, right? So let's replace. N is given 100. B is given 0.2. Area is given 24 times 10 to the minus 4, right? Times cosine theta. I didn't replace theta because the coil is turning or rotating inside the magnet. So theta is variable and consequently the variable quantity is cosine theta. So we get equal how much? 48, because 24 times 2, 48, times 10 to the minus 3 cosine theta, right? We need minus phi prime. So here phi prime is equal to minus derivative, we make the derivative here. This is phi, we make the derivative. What is the derivative of cosine u in mathematics? Minus sine u times u prime, right? So minus 48 times 10 to the minus 3 sine theta. This is sine u times u prime means derivative of the angle, which is theta prime here, where theta prime is 1200 revolution per minute. But you know that theta prime must be expressed in radian per second. So let's change theta prime. Theta prime equal 1200. Per minute means over minute, we change it into second. So it becomes 20 revolution per second. Multiply by 2 pi times 2 pi, you get theta prime equal 40 pi radian per second. So replace it here, we get phi prime is equal how much? Minus 1.92 pi sine theta. Okay, this is phi prime. Now E average equal, not E average, E equal minus phi prime, which means that E equal 1.